Good morning. Let's talk about Taylor series. So before we've been talking about series, and they've been kind of abstract. We really haven't seen what the value of them have been. And Taylor series is when it kind of all comes into focus, like that little laser beam death thing that kills the superhero by the villain, but never actually does. Well, this giant super laser beam is actually effective. So Taylor series, what it does is it allows you to approximate pretty much any function with a power series and basically x squareds. Maybe you've heard of Fourier series. Fourier series is the idea where you can model any function with a whole bunch of signs. There's different weights and different proportions, but the idea is you can take a whole bunch of sine curves, put them together in just the right way to make anything. Same thing goes with x squareds, more or less. Being a little generous there, but the Taylor series is something you can learn. We're going to learn now, as opposed to Fourier series, which will be probably later, not in this class. And so I'm going to present it to you without really any derivation or even really the motivation of where it came from. I'm just going to be like, formula. And then we'll do the formula a few times to provide a sufficient number of warm fuzzies that it actually works, and then we'll go on from there. I know it's probably terribly disappointing, but we're all about effectiveness here and not about deep, zenful understanding, meditations, and such. So I'm going to write it sort of like this. So f of x is approximately n equals 0 to infinity of f, and this is the to the derivative of a. Don't worry, I'll explain it more in a sec. Whoop, to the n all over n factorial. Now it looks pretty big and imposing. Trust me, it's not. Yeah, maybe it is. I don't know. When your memory is as poor as mine, it probably is a little imposing. So this here is number derivative of. So you can think of this as f of x, or f prime of x, or f double prime of x, triple prime of x. I don't know if they do 4. They normally start doing something like 4. And then they go on as such. So that's what that little f to the n means. It's not really an exponent, it's a derivative thereof. A is the point about which you do the approximation. So if you've seen, if you look at a picture of the globe, you realize, well, that it's flat, but the globe is more spherical. Not perfectly spheroid. I think it's spheroid. Is that the word? I think it's spheroid. Anyway, the globe is three-dimensional, but they put it on the two-dimensional flat thing. And there's a lot of distortion involved. Well, one of the things is different projections have different levels of distortion, but you can also choose where that distortion is. So if you notice, there is less distortion in size near the equator, but you look at Greenland and wow, Greenland's going to conquer the world. Well, Greenland is pretty big, but it's not actually as big as it's portrayed on most maps because of the way the projection is. It's so far north that the size of Greenland is greatly distorted. That's what A is about here. A is where we're doing our approximation at. So if we're trying to find, for example, e to 2.2, whoop, whoop, grab the pen, wow. I'm not actually going to find it. Then we may want to do we may want to center our approximation at for e to the x at a equals 2, because that way it would be closer than a equals 0. And since if we center our approximation closer to what we're actually looking for, it will on average mostly probably be a slightly better approximation. So that's the idea of A. A is often just taken to be 0. I think that's called the Maclaurin Series, where A equals 0. Is he Scottish? Oh, I'm going to feel bad now if he's not. That's okay. 1700s, 1800s? 1600s. So a equals 0 is a common. Oh, I'm gonna have to look this up now. I'm sorry, guys. Wait one. Okay, so it is the Maclaurin series, named after the Scottish mathematician Colin Maclaurin, who made use of it in the 18th century, so 1700s. So I wasn't that far off. Granted, I guessed it, I think, 300-year span. So generally when you guess a 300-year span, you'll probably be close. So, and that is where a equals 0. It's kind of disappointing that, like, all this math that you're learning now, you're like, I'm so smart, I'm learning math and calculus. It's like, yeah, people have been doing that for hundreds of years. Kind of makes you question yourself as a person. Oh well. So that is what a is about. For pretty much all the examples I'll pretty much just say a equals 0. It just makes things, even though it makes things more accurate, for demonstration purposes, it makes things more complex. Because when you're talking about x to the minus a to a power, then you get this binomial theorem, coefficients, not fun. Okay, to the n, and we divide by n factorial. And this is the Taylor series formula. So I'm just going to jump straight into an example. So let's say, for example, we want to know what sine of x was. So we would do find sine of x. Well, start with f of x, or approximate sine of x. So we would start with finding the derivatives. So f, I'm going to use 0 here, just to be extra explicit. My notation will kind of change as I go. I'll start off very obvious, very explicit, and then kind of leave a few things to be implied later on. But the first go around, it's kind of nice to be very, very slow and methodical. So sine of x is sine of x. F prime of x is cosine of x. F to the second of x equals negative sine of x. A little bit more real estate, a little bit more board. F to the third derivative is cosine negative of x. And then to the fourth derivative gives us back to sine of x. And the circle of life repeats. Okay? So now we're going to plug in, since we're looking for f of a, we're going to plug in f of a. F. And it's kind of nice to do it in this format where you do all the derivatives first, then you plug in all the derivatives, because it keeps you in the same mindset. You don't keep changing, you don't keep retooling your mental machine, so to speak. So sine of, we're going to say that about a equals 0. We're going to do our approximation at 0. Sine of 0 is 0. Cosine of, so a is 0. I should probably put 0 there. Oh, there we go. Same thing, because a equals 0. Cosine of 0 is 1. F from the second derivative of 0 equals negative 0, which is still 0. F third derivative of 0 equals negative 1. F fourth of 0 equals 0. Okay? Now we're going to do the binomial portion. So this part right there. X minus a, which is 0, to the 0 equals 1. X minus a to the first equals x, because a equals 0. Then this will be x squared, x cubed, x to the fourth. Okay? And then, just as an example here, x minus a to the third, x minus a squared, x minus a to the fourth. Okay? And then, just to round everything off, I will put in the what is that called? When you do the exclamation point thing. I should know this. Did I just say this earlier? Factorial? No, it's not factorial. Yep, factorial. Man, I've been using it forever. How do I not know that? Outrageous. Outrageous. 1 factorial, 2 factorial, 3 factorial. Man, how do I get out of bed in the morning? Remember how to breathe. Okay. So here is all the data we need. And now we're going to put it together. Now, this might be a little excessive, but in the grand scheme of things, when you're actually trying to find one, maybe leave out this step here and just write the x's. But for the rest, I'd recommend writing it out depending on how much time you're allowed. Because this is, you're like, wow, why don't machines do this? Well, machines do this, but until you're, understand the process, you'll do it a few times on your own. And maybe you'll be stuck on a deserted island and have to find out, some sort of something. Okay, focus. So we have the first portion. So sine of x is approximately 0 times 1 all over 0 factorial. 0 factorial is 1, by the way. There's no real justification for why it is, other than the fact that it seems to work well, which is a good enough justification for anything in life. Divided by 1 factorial plus 0 x squared over 2 factorial plus negative 1 x cubed over 3 factorial plus 0 x to the fourth over 4 factorial plus ... Okay, so simplifying this slightly, we find, I'll still use approximately, x plus minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus ... Okay, so here is the pattern that sign follows. And some things to note. Sine of x. And I could probably actually use the equal sign since it goes on forever and then becomes an infinitely good approximation, which is the same as being exactly equal. So some things to note is we have now just kind of sort of converted sine of x into all x's to powers of x. And this can be really useful because, again, stuck on a deserted island, how are you going to calculate sine of x? Well, you can calculate powers of x, which is kind of nice. It takes a while, but you can do it. And so this gives you a way of looking at sine of x in terms of just x's, powers of x, which is really cool. And just to show some of the value of this, I assume maybe you should have, maybe you didn't. You've heard of the small angle approximation, or a small value of x, I'll say theta, sine of theta is approximately theta. And you're like, oh, where does that come from? You probably have seen this before. And if you have used like any old school calculators, the less smart ones you probably are using right now, and you try to do sine of like 0.004, like a small number, it would give you some crazy answer. Well, it turns out that just saying sine of 0.004 in radians is actually pretty much just 0.004. And one of the justifications of why that is what you're doing is you're really just using the Taylor approximation, the Taylor series, and you're using the first term, we call it a first order because x is the first, Taylor series approximation. So when you're saying sine of theta equals theta, Well, for small angles, you're true because, kind of, sort of, because when you have a very small number and you cube it, it's going to be pretty small, pretty darn small. And in some ways, you can be like, well, that's negligible. And so the approximation of sine of theta equals theta for a small theta comes from the Taylor series approximation. So this is the Taylor series for sine, where you see that it is it has odd numbers and then it's divided by the factorial of the same power that x is risen to. One other thing to note is that it is odd. If you look at, it's an odd function. So if you look at sine, it's not symmetrical over the y-axis. And you see that with like some values it is. So if you look at like x squared, that's supposed to be more rounded, y equals x squared. You can put in +1 or -1 and you'll both get the same value of y. Not true with x cubed, which looks something kind of like this, where you put in 1 and you get +1, you put in -1, you get negative. So sine is an odd function. It operates more like x cubed. And by looking at its Taylor series, it's like, oh, that kind of makes sense because they're all odd functions in here. And that is sine of x. Now, your thought process is, oh, should I just memorize these? Yes. There is a handful of Taylor approximations that you should memorize. One of them is sine of x. I'm going to write this up here real quick. Sine of x is approximately, though I could probably use x cubed over 3 factorial, x to the 5th over 5, and then it continues on as such. So then I'll go back to negative x to the 7th over 7 factorial, and so forth. Okay, so now you can probably see where this is going, but I'm going to do cosine next. Now, let's see. Whoop. So I'll erase all this. Clickety-clack. Whoop. Green. You can probably kind of see how cosine goes, and I know you guys are smart enough to do this on your own now you've seen the process, but the probably 3 that you really kind of need to know and kind of go well together are sine of x, cosine of x, and then e to the x. So it's probably worth our time to go through those. And then we'll go on to a couple more exciting examples. So for cosine of x, going through the process, f of x equals cosine of x, and this will be about a equals 0. F prime of x equals, is it negative sine of x? I think it's negative sine of x. We'll see. F second of x equals negative cosine of x. F to the 3rd of x equals, back to sine of x. There we go. And then I know that the derivative of 4th of x equals cosine of x. And we're back to the beginning. Okay? Not everything will loop at after the 4th derivative. That's just a cosine, sine, imaginary number type thing. So f of 0 equals 1, f prime of 0 equals 0, f second prime of 0 equals -1, f third derivative of 0 equals 0, f fourth derivative of 0 equals 1. Okay? And then we have where x equals 0, so I have x to the 0, x to the 1st, x squared, x cubed, x to the 4th. And then for factorials, we'll have 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. I don't know if I ever actually explained what factorial is. So this factorial here is just 1. This is 2 times 1. This is 3 times 2 times 1. This is 4 times 3 times 2 times 1. Just in case. You probably knew that, but just in case you didn't, I will throw that out there. Okay, so now try and get the big view here. Blue. So we'll do this times that divided by that. So we'll start with 1 cosine of x is approximately 1 over 0 factorial. 0 factorial is 1 plus 0 x over 1 factorial plus minus x squared. Oh, check real quick. Yep. Minus x squared over 2 factorial plus 0x cubed over 3 factorial plus x to the 4th over 4 factorial. Minus, okay. And then continues on as such. So then simplifying things, we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial and so forth. Okay. Do that, do a copy paste, delete this, delete that. And so for cosine of x, we have very similar to sine of x, except this time, I used more terms. And you can see that this is an even function. If you put in a -1, you'll get the same answer as if you put in a +1, or pi over 2, or pi over 4. Delicious. And so, yep, pretty good. And it's interesting too, like if we talk about the small angle approximation for sine, you could kind of sort of say the small angle approximation for cosine is just 1. And a small angle of cosine? Nah, it's probably 1. Meh. Cosine of 0.02? Meh, 1. But if you want to be more accurate, then you could do 1 minus 0.02 squared over 2 plus 0.02 to the 4th over 4 factorial, which is what, 6 times 4, which is 24. And so you can get as accurate as you want, and you get pretty accurate pretty fast. So this is a very quick way, very non-intensive calculation-wise way of solving for sine of x and cosine of x. Okay? Now we'll do e of x. E of x is, I know, you're like, so many. I know. There are some things in life that are worth seeing, and sine of x, the Taylor series for sine of x, cosine of x, and e of x are kind of those. I sympathize with your plight, but I'm going to do nothing to help you. In fact, I will probably make it worse. E to the x. Okay. And we'll say that a equals 0. Maclaurin series from Colin Maclaurin, the Scottish mathematician from the 17th century. As we learned, I kind of sort of suspected, but we learned. I love Wikipedia. It's like the best choose your own adventure book ever. All right, focus, focus. F of x equals e to the x. F prime, single prime of x equals e to the x. F double prime of x equals e to the x. Okay, I can probably go these quicker. I see the pattern. And you can see how my notation is going quickly sliding downhill. Equals e to the x. F of 0, which is same as f of a, equals e to the 0, which equals 1. F prime of 0 equals 1. F second derivative of e to the 0 equals 1. F third of 0 also equals 1. And f to the fourth derivative of 0 equals 1. Okay? X to the 0 equals 1. X to the first is just x to the first. X squared is x squared. X cubed is x cubed. And x to the fourth is x to the fourth. N factorial, which is 0 factorial. Then we have 1 factorial, 2 factorial, 3 factorial, 4 factorial. Okay, so now we have all the data required. We will bring this home with my bring it home color, blue. Blue has just recently become my bring it home color. I love blue. Everyone loves blue. Well, everyone except Ohio. Let's see here. Hop, 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 hop. Okay. This is the, if you pause too long, you kind of lose the momentum. So it's this times that divided by that. So this will be 1 times 1 divided by 0 factorial, which is also 1. And then we'll add on to that with 1 times x over 1 factorial plus 1 times x squared over 2 factorial plus 1 times x cubed, that's supposed to be a 3, cubed over 3 factorial plus 1 times x to the fourth over 4 factorial, and continue as such. So we know that e to the x equals 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus dot dot dot. Okay, and so this is a Taylor series approximation for e to the x. Should have had a different color because now it's like sign looks like the odd. Ooh, can I change the color? Green. It does not. Cyan? No. Orange. Yeah. Purple. There we go. Purple. Okay. And so that is e to the x. So at this point, you're probably like, are these true? Should I Google this? Do I trust this guy? This random person on the internet? I like your lack of faith. It's the questioning attitude. It's good. Very nice. So to give you a warm fuzzy, we'll look at another equation. So let's say 3x cubed, and we'll subtract 5x squared plus 2. I did not actually have that one pre-planned. It just, bam. We'll see if this works. So we should be able to approximate this using x squared and coefficients. But it already has x squareds and coefficients, so ideally we should get the same thing back using this formula? Maybe? Possibly? We'll see. If we don't, I'm real trouble here. I'll go do it. We'll approximate this about a equals 0, but you could choose another a. If I was a better person, I would choose a equals something else, just to kind of show that it works for other things. I'm not that creative. Sorry. Okay. So we have f of x equals 3x cubed minus 5x squared plus 2. F prime of x equals 9x squared minus 10x. F to the second derivative of x equals 18x minus 10. So that looks like a 16, so I will adjust it. Okay. F to the third value of x equals 18. I'm going to clean the board up a little bit. So let's see. All right, we got these memorized. You can write them down. They're probably worth writing down, and you can Google them later. Whoop. Just help keep the board a little bit clean. Okay. And let's see. Let's do the fourth. Back to purple. F fourth derivative equals 0. And then so forth, they'll continue to equal 0. Write the fifth one down just to make everyone feel better. 0. Okay? Okay, and now we need to change colors. We don't actually need to change colors, but it soothes my soul. I think this one will equal 10. Negative 10. Good catch, guys. I know, my notation is terrible. And then after the fourth is 0. And then, so now we need to find the x values. Whoop, whoop. Will be x to the 0, x to the 1, x squared, x cubed, and those will be x to the fourth, x to the fifth, but those will be 0. I'm going to take these off just because we already know that they're going to be 0. And whoop. And then we'll have the factorials, which factorial of 0 will be 1, factorial of 1 will be 1, factorial of 2 will be 2, and factorial of 3 will be 6. And then, so now we can approximate f of x with, okay, so we do this number times that number divided by that number. So it'd be 2 times 1 divided by 1 plus 0 times x divided by 1 plus minus 10x squared divided by 2 plus 18x cubed over 6. So simplifying these things and moving the highest powers to the left, we have, that goes to 3x cubed minus 5x squared plus 2, which is our original equation. Huzzah! Win! So the Taylor series does work. This magic formula is, well, I guess that doesn't prove it isn't magic, but it proves that it's at least effective magic. It's at least effective. So we'll leave it at that. So clean up the board real quick. A little bit of confidence, okay? Yep. Pow. So now would be a good time for us to do a couple of examples, because you're kind of wondering, well, how big a deal is this going to be on an AP exam? What kind of questions they're going to ask? It seems like a lot of work to do just for an AP exam. And it's true. They're very rarely going to be like, find the Taylor series of this function. Because most of the Taylor series functions that you're supposed to know will be sine of x, cosine of x, or e to the x. Maybe natural log of 1 plus x. There's a few other common ones. But for the most part, they'll ask you things that you're always supposed to have memorized. Or they'll ask you in kind of a funny, not funny way. There's some good ways of testing your knowledge on this. So we'll go through a few problems where things you might kind of sort of see in life. So, as such a possible example, let f be a function having derivative of all orders, okay? Infinitely differentiable. So that says basically, it's not going to be the sort of thing where you try and find third derivative of f and the universe explodes, which is a requirement of a Taylor series of the universe not exploding due to derivatives not existing. For x greater than 0, such that f of 3 equals 2, f prime of 3 equals -1, f double prime of 3 equals 6, and f triple prime of 3 equals 12. Which of the following is a third-degree polynomial for f about x equals 3? Okay, so they said about x equals 3. So this is a equals 3, and they gave us the f of a's, because there's 3 in there. That's the a. So that's that portion right there. And so we're just going to write it out from the beginning. So f of 0 is 3, which is 2, times 1 over 1 factorial, 0 factorial. And this 1 is actually x to the 0. Start over. 2 times x to the 0 over 0 factorial. There we go. And then we will add to that -1. So I'll subtract 1 times x, x minus 3. So I was so busy doing Maclaurin series that I got thrown off by a not equaling 0. Okay, minus 1 times x minus 3, because a is 3, to the first, all over 1 factorial, plus, and this is the second derivative now, 6x minus 3 squared over 2 factorial, plus 12 times x minus 3 cubed over 3 factorial. Okay? And we'll do a little simplifying. Yep, because it looks like they have nothing in the denominators. So we'll try and get rid of our denominators as well. So this is 2, which becomes 3. This is 6, which becomes 2. And did they expand them? No. Okay. So this will be 1. So it'll be that we can just get rid of. So it'll be 2 minus x minus 3, parentheses, plus 3 x minus 3 squared, plus 2 x minus 3 cubed. Whoop. Do this. Not quite. Oh no. Where'd my cube go? I'm worried that I can't make an appropriate box to bring it over. It's okay. We'll just zoom out slightly. So we have 2. Oh, they all have 2. Psh. Now that's anticlimactic. Okay, so first number is correct. X minus 3. I'll say no, because I think they're trying to do the Maclaurin series up here, where a equals 0, where a specifically does not equal 0. So then we have x minus 3, check. And then we have 3x, so this one's gone. And there was this one here. So what they're doing on this one, I think, it's as if you couldn't remember a formula and instead of n factorial, you thought that was just n, then you would get 4 for this answer instead of 2. And that's what they were testing you on there. They're trying to test that you know that it's over n factorial, not just n. And so E would be the correct answer on this one. Seem reasonable? So have formula, give you data, put it together, get answer. And this is like, hey, a couple minutes? Yeah, we could do that. We might have even done this problem in 2 minutes. And I'm pretty darn slow. So that's an accomplishment. Okay. Clean up board. Get rid of n factorial equals n. That arrow, trying to delete it. Get rid of the 3. No one likes you, 3. Go away, 3. Oh, that's harsh. I'm sorry, 3. All right, get the next problem. Okay. For x greater than 0, the power series, 1 minus, I think that's just x squared over 3 factorial, plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial plus such and such equation. I'm just going to ignore the equation for now because though it's probably technically correct, I don't have that much time to think about that. Converges to which of the following? So when it says converges, you're thinking, oh, convergence something, something, something. Another way of thinking of that is this is an approximation. And so if you think of like Riemann sums, making boxes smaller, infinite number of boxes, the Riemann sum can converge to, depending. If you have infinitely thin boxes, it'll converge to the integral. That's probably a bad way of thinking of it. This is basically asking the Taylor series approximation. So which one of these is the Taylor series for that? So let's see here. So cosine of x, that is, as we know, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot, dot, dot. Okay? Sine, so that's cosine of x. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot, 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 dot. E to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial dot, dot, dot. Okay? So we probably think that this is not e to start with because we don't have any negatives. But they have this over here. Man, that's convincing. So e to the x squared would be, so we have e to the x squared, basically be putting x squared in for x. So you have 1 plus x squared plus x to the 4th over 2 factorial. But then 4 factorial minus 2 factorial isn't quite right. Man, that is confusing. I did not expect to. Okay. So it's not sine of x, it's not cosine of x, because cosine of x has the same numbers. So sine of x and cosine of x have the same number for the exponent and the denominator factorial. If we try this one, we get sine of x, which is x minus x cubed. Oh, that might, okay, I think that one works. So if we divide this by x, if we have sine of x divided by x, then we're going to have, what is it going to be is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Divide each of these by x, and you have 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial, and minus, yep, I think this is going to be the one then. So the tough part about this problem is, and then I'm just going to ignore the e's because that's going to be a lot of work to figure out what those actually mean. So we could totally do it. We just replace the x with x squareds here. But yeah. The difficult part about this is getting the correct thought process. So for this, I'd basically write out, I'd see this, I'd be like, all right, Taylor series. And be like, look at the answers, be like cosine, sine, and e to the x. I was like, got those. So I would write those down, probably just the first 3 terms, so you kind of get the idea. And then from there, I would just look for the easiest one and try that. Be like, cosine of x? No. Sine of x? No. And then this is probably the next easiest one, so I'll try that one and just see if it works. And it did, so then we kind of got lucky. But there really isn't a good methodical, well, we're going to start here and go here. This is put all your knowledge in a box, shake up the box, look in the box, and maybe it's what you want. There is no, like, this is how you do this, this is where you end. There's a certain, I think the mathematicians are like, well, you solve it by inspection. It's like, you just look at it and you know the answer. Or guess and check, if you will. So I would do a combination of guess and check and then just throwing down the knowledge you have, and hopefully you get it. I know that sounds like terrible advice, but with a couple minutes of guess and check, you could probably get this one. So you have all the requisite knowledge, and you can know the right answer when you pick the right answer, but knowing the right answer and then looking for it out of the solutions would be very difficult. This is one of those, you look at the solutions and you see which one solves your problem, as opposed to looking at the problem, getting the solution, and then finding a solution from the set given to you. Seem reasonable? Yeah, this one's a little bit tough. I will acknowledge that. But yep, knowing sine of x, cosine of x, and e to the x are essential. Well, essential is a strong word. Gosh darn useful is probably the more accurate representation of how vital it is to know it for the AP exam. Okay, so we'll do one more problem. I like multiple choice problems. These things are just more fun, exciting, little teeny puzzles. Crystal light. So delicious. Okay. So the Maclaurin series for the function f is given by f of x equals this. Okay. What is the value of f of 3? Okay. Maclaurin series means that a equals 0. Okay. I'm just going to write out the first few terms and see if it magically clicks. So f of x equals negative x over 4 to the 0 plus negative x over 4 to the first plus negative x over 4 squared plus negative x over 4 cubed plus negative x over 4 to the 4th plus negative x over 4 to the 5th. You're probably like, wow, why did you go on so long? It's like, well, because I don't know what I'm doing. So I was hoping that maybe if I just wrote out a few more, like some magic thing would just click and I'd be like, oh, well, this is the answer. No, it didn't. It really, nope, lost. So simplify this. This is 1 minus, and then we're plugging in 3 for x. So minus 3/4. This is plus because negative 3/4 squared is same as 3/4 squared, minus 3/4 cubed plus x, nope, 3/4 to the 4th minus 3/4 to the 5th. And then it goes on. So I'm just going to plug these in since we have numbers and see if one of these answers is kind of sort of almost correct. And see, 1 minus 3 divided by 4 plus quantity 3 divided by 4 squared. I'm going to do minus there. That way I can just do like this. Cubed. I know you can't do this on your calculator and it's not really fair for me to lord it over you. That's okay. I never claimed to be a fair tyrant. I never claimed to be a benevolent dictator. let's see. So if we plug this in, 0.47. And that's, let's make sure they alternate. So we got 0, 1, 2, 3, 4, 5. Okay, so I got 0.47 equals 0.47. And then we're going to add one more. So this is for 5 iterations. We'll do 6 iterations. And, whoop. So do copy, paste, change the 5 to a 6. And we have 0.65. So what's happening is it's alternating between, that's not a good drawing. So we have some answer here, and this is going somewhere like this, and it's homing in on the correct answer. And so we know the correct answer is going to be between 0.47 and 0.65. So we can look up here and be like, okay, it's not negative. It's not 4. So we're basically down to this one. 4 divided by 7 is... I feel bad erasing all that. I'll just copy it so I have it for later in case I want it. 0.57. That looks like a contender. So we have 0.5, oh, I'll do it this way. 0.57 and 13 divided by 16. That's like 3/4, I think. 0.81. 0.81. Okay, so we know the answer has to be between these two, and the only answer we have that is between those two is 0.57, which is 4/7. So the answer is going to be 4 divided by 7. So this is, I guess, kind of a semi-educated guess and check method, which I try to avoid when I can, but that seemed to work out reasonably well and reasonably quickly too, because so they gave us the value we wanted to look for. They gave us a way to calculate the value, and we just plugged it in and went. So, yep, minimal calculus involved. So just understanding what they're saying in the problem, and then plugging in some numbers and going from there. Sounds good. I like that one. I do kind of like that one, even though I feel kind of cheap and dirty by the way I solved it. That's okay. I'm good with that. All right, so this is the Taylor series. I will talk about some more Taylor series things next time. It's really cool when you get like the x squareds going, and it allows you to do some cool things with integrating and derivatives. So I'll talk a little bit about that just because I would be remiss if I didn't. And it's useful. Yes, very useful. So we'll go a little bit over that next time, then we'll continue on to some of the other topics. Thank you for joining me. See you guys next time.